So to continue, we have now identified our case of S, which is 96, and case of C is 84. So from the equation, case of S plus case of C, which is 180, so it gives us 180. And this is based on table 3.2 and 3.3. So we have identified that the design speed for the value of case of S, which is 96, is 50 miles per hour, and the design speed for case of C is 50 miles per hour also. So 50 miles per hour will be the design speed, and the total of K value for case of S and case of C is 180. And we have to determine the curve length. So the curve length, your L sub S is equal to K sub S times A, and this will be equivalent to 96 times 6.667. And L sub C, which is equivalent to K sub C times A, this is actually equal to 84 times 6.67. So this gives us a value of 640 feet. That's one. The value is 560 feet. So this is the length of the sag curve, which is 640. This is the length of the crest vertical curve, 560. So we have now our value for, if we're going to total this one, that's 640 plus 560, that is equivalent actually to 1,200 feet. So now we can identify our PVIS. So the PVI for the sag vertical curve. So PVI for the sag vertical curve actually is equal to the PVC of the sag vertical curve plus the distance, or plus L all over 2. So L over 2, that is for the sag vertical curve. The length of the sag vertical curve is 640. L over 2 is 320, or that is 3 plus 20. So this will be equivalent to 0 plus 3 plus 20. So this gives us 3 plus 20.0. This is for the station of PVI. Now for the sag vertical curve. For the PVT, you have to take note that the PVT for the sag vertical curve is actually equal to the PVC of the crest vertical curve. So therefore, if we're going to have now the PVC, this will be actually equivalent to 6 plus the PVT, which is equivalent actually to the station of PVI of the sag vertical curve plus our L. So our L for the sag vertical curve is 640, or that is 6 plus 40. So this is 0 plus 6 plus 40. So we have here 6 plus 40. This is the station of PVT. The station of PVT for the sag vertical curve and PVC for the crest vertical curve. Now we can identify the PVI. So the PVI, we have to take note that the PVI for the crest vertical curve is actually equal to the station of PVI or PVC for the, okay, that will be equivalent actually. This is 640. The station is 6 plus 40 plus 5 plus 60. So that will be the station of PVC for the crest vertical curve plus the half of the length of the crest vertical curve. So this is 6 plus 40 plus This is L all over, L, the length here, 560 divided by 2 is 320. So that will be 290 rather. So this is plus 290. L sub C all over 2 is 560 all over 2, which is 290, or that is 2 plus 90. So that is plus 2 plus 90. So this gives us a result of 9 plus 20. So you have now your station at PVI for the crest vertical curve. And the station for PVT for the crest vertical curve actually is 12 plus 0, 0. So you have now, it's already given. So therefore, for the elevations, the elevation of PVC for the sag vertical curve is actually the elevation for PVI for the sag vertical curve, and that is actually equal to 100 feet. And for our PVSI for the crest vertical curve, and actually that is equal to the PVT of the crest vertical curve. So that is actually equivalent to 140 feet. So therefore, the elevation for PVT for the sag vertical curve and PVC for the sag vertical curve can be computed as, so this will be equivalent actually to, you have 100. So actually this is equivalent to the PVT for sag vertical curve is actually the PVC for the crest vertical curve, and that is equivalent to 100 plus, this will be the equation. 100 is the this is our the elevation of the tunnel, then plus our y sub f, the final offset. So A L S all over 200. So this gives us 100 plus 6.667 times 640, then divide this to 200, and this will give us 121.33 feet. So you have now, so you have to take note that if this is our curve, so we have here the tunnel, so this is the BC for the sag vertical curve. This will be the location of PVI for the sag vertical curve. Somehow this is our PVT for the sag. This is also PVC for the crest vertical curve. And this is our PVI for the crest vertical curve. And this will be our PVT for the crest vertical curve. So somehow, if we're going to observe, if we're going to draw a tangent line, so it will meet at certain point here. So you have here at certain point it will meet somehow. This is our PVI. So that is the main reason why our PVC actually for the sag vertical curve is equal to the PVI for the sag vertical curve. Similar also, because the intersection, if you're going to draw the intersection, the tangent line, the intersection is almost of the same level to the PVC for the sag vertical curve, and same level also for the PVT for the crest vertical curve and the PVI for the crest vertical curve. So which means that our PVI for the sag and the PVC for the sag, they have the same value. So that is 100 feet, because the elevation here for PVC for the sag vertical curve, that is the elevation of the tunnel, which is 100 feet. Similarly also, the elevation for PVI for the crest vertical curve, because if you draw the tangent line, it will intersect here, which is of the same level with our PVT for the crest vertical curve. And the elevation here actually is equivalent to 140. So if this is 100, so this one is 40. So that is from here. So which means that from that portion, so the PVI and PVT, the elevation to that is also 140 feet. So therefore, now for our PVTS, this is our PVTS and our PVC for the sag, PVTS for the sag and PVC for the crest vertical curve. Actually, that will be equivalent to, if this will be our tangent line, so we're going to make use of our offset. So that will be, if we're going to have your offset, this will be our y of f. So that will be 100, elevation is 100 plus the equation for our offset, which has AL all over 200. And similarly also, it will, since the location of PVT for the sag and the elevation for PVC of the crest vertical curve is of the same point. So we have now the value, which is 121.33 feet. Okay, let's move on to passing sight distance and crest vertical curve design. So in addition to stopping sight distance, in some instances, it may be desirable to provide adequate passing sight distance, which can be an important issue in two-lane highway design. So the passing sight distance is actually a factor only in the crest vertical curve design. So which means that we consider the design for the passing sight distance compared to the sag vertical curve, since for the sag vertical curve, the sight distance is unobstructed, looking up or down the grade, and at night, the headlights of oncoming or opposing vehicles will be seen. So for this one, in determining the sight distance required to pass on crest vertical curve will apply. So the driver's eye, which is our H1, will remain as 3.5 feet, and H2 will now be set to 3.5 feet. So the value for H2 is assumed value for the portion of the vehicle's height to be visible such it can be recognized an opposing vehicle to a driver performing a passing maneuver. So for this one, if we try to substitute the value for H, letting our sight distance S equal the passing sight distance PSD, so we have here equations to solve for the minimum length of the curve. So when our passing sight distance is less than the length of the curve, our minimum length distance, L sub m, is equivalent to A times PSD squared all over 2,800. And if the passing sight distance is greater than L, our minimum length of the curve is equal to 2 times PSD minus 2,800 all over L. So where our L sub m refers to the minimum length of vertical curve, and our A refers to the absolute value of the difference in grades, which has G sub 1 minus G sub 2. And of course, our PSD is the passing sight distance. And in the case for the stopping sight distance, it is typically assumed that the length of the curve is greater than the required sight distance. So which means that L is greater than PSD. So we have the formula for our K, which has PSD squared all over 2,800. And our K, of course, is the horizontal distance that is required to effect a 1% change in the slope, and PSD is the passing sight distance. So we have here a tabulation. So for the minimum distances needed to pass at various design depths along with the corresponding K value as computed in the equation presented, we have here table 3.4, which is the design control for crest vertical curve based on passing sight distance. So this is based on the AASH2, or the American Association of State Highway and Transportation Officials. So we have to identify our design speed so that we could identify our PSD, or the passing sight distance, as well as the rate of the vertical curvature, which has our K.